Hi, and welcome to the Aimtec Academy, the best place to learn about Aimtec power supplies as well as the power supply industry as a whole. Today we're going to be talking about a very broad topic, and that is power conversion for railway. Now, whether it's refurbishing an old system or redesigning a new one, Aimtec has your power needs covered. Let's hop in the course to find out more. Welcome to Aimtec's training course on railway products. Trains have unique requirements because they are subject to operating in harsh environments that subject them to high temperatures, high humidity, vibrations, and high salinity. Modern trains are equipped with various electronic devices which need to be powered in a reliable way in order to prevent certain systems from failure. There are two types of power sources for trains that is responsible for the propulsion. The first one is the electrically powered train. This type of train is powered from the overhead power line through the pantograph. The transformer steps down the high voltage and feeds the power into the main AC-DC converter. Two DC-AC inverters located on the main converter convert the DC power back to AC. One supplies the traction motor while the other supplies the auxiliary power. AC power provided by the DC-AC auxiliary inverter is converted into three-phase and powers the HVAC and lighting directly. Finally, an AC-DC converter converts these three-phase AC into DC, then powers the important electronic devices and control systems. A battery is connected to ensure the continuous operation of the critical control devices. Now moving on to the diesel powertrain. This gets its power from the diesel engine and two alternators. Unlike the electrically powered train, the diesel-powered train does not share the main AC-DC converter. Instead, the diesel-powered train has two independent power systems, one for traction and the other for auxiliary power. Besides the aforementioned difference, the rest of the power layout remains identical to the electrically powered train. So where do Aimtec products actually fit in? Depending on the manufacturers of the train's auxiliary power voltage level can be either 24, 36, 48, 72, 96, or 110 volts. 110 and 72 volts being the most common voltage levels, as higher voltages lower the current and reduce the wiring space and height. However, most of the electronic devices require 3.3, 5, or 12 volts to actually run. This is where Aimtec railway power supplies can step in and help convert the higher auxiliary voltages into voltage that can power the electronic devices. On screen we have two examples of very common applications. One is the pneumatic plug door, and the other is the infotainment. Now moving on to what actually makes a railway power supply a railway power supply. To qualify as a railway power supply, the EN 5155 Railway Applications Electronic Equipment Used on Rolling Stock standard needs to be met. It specifies the minimum requirements for railway electronics based on the input voltage, mechanical performance, thermal performance, isolation, and electromagnetic compatibility. Now we're going to walk through the different requirements mentioned here. So to begin, we're going to be looking at the input voltage. The auxiliary power drives multiple plug doors, motors, and relay coils. Since there are a number of heavy loads connected to the auxiliary power, the voltage is expected to fluctuate. The table seen here shows the EN 5155 requirements on input voltage. Railway electronics need to be able to accept wide input voltage ranges of 0.7 to 1.25 times the nominal voltage. So in this case, if we look at the first row, where we have 24 volts of nominal input, the continuous input needs to be between 16.8 and 30 volts. The brownout needs to be of 0.6 times the nominal input voltage. So in this case, we take 24 volts, multiply it by 0.6, and that gives us 14.4. And the transient is 1.4 times the nominal voltage. So again, with our 24 volt example, this gives us a transient of 33.6. Moving on to the mechanical requirements, as trains are subject to extreme vibration, The standard also specifies the minimum mechanical requirements that railway electronics need to meet. There are 4 different levels of mechanical requirements based on where the devices are installed. Category 1, Class A, is for components installed directly onto the car body. Category 1, Class B, is for components installed on the underframe, which is attached to the car body. Category 2 is for bogie-mounted components, and Category 3 is for axle-mounted components. Generally, Category 1, Class B requirement applies unless otherwise specified. Next, moving on to thermal requirements. Thermal requirements change based on the location and the type of components. There are 6 temperature classes. OT stands for operating temperature class. OT1 and 2 apply to components installed in the passenger cabin. OT3 and 4 are from components installed in technical cabinets. OT5 and 6 apply to semiconductors. Generally, OT3 requirements applies unless otherwise specified. And as you can see in the table, depending on the operating class, we have various temperature ranges that are required. Next, moving on to the isolation requirements. The standard specifies the minimum isolation and insulation requirements. The minimum insulation value is of 20 megaohms under the 500 VDC test. The isolation requirements are shown in the table. So if we're below 72 volts, the required isolation is 500 VAC or 750 VDC. Between 72 and 125 volts, we're looking at 1000 VAC or 1500 VDC, and so on and so forth. The test voltage should be maintained for 1 minute for a typical test and 10 seconds for a routine test. And finally, moving on to EMC. The auxiliary power battery is usually placed at the front or rear of the train. This results in the power line having to travel long distances before reaching the target devices. In this case, the long power line acts as an antenna and will pick up noise from the traction motor, main transformer, and pantograph. The personal electronic devices carried by the passengers also worsens the situation. To avoid railway electronic devices from being affected by electromagnetic interference, EN 50155 refers to the EN 50121-3-2 and regulates the minimum EMC requirements. If you want to learn more about these different EMC requirements, please look at our course on EMC. But just as a quick reminder, in this table we can see that EMC is divided under EMI and EMS. And under EMI we have conducted emissions and radiated emissions, and under EMS we have electrostatic discharge immunity, radio frequency electromagnetic field immunity, electrical fast transient burst immunity, surge immunity, and radio frequency conducted disturbances immunity. And the standard dictates the required values for each of these. Now we're going to be moving on to actual application examples using Aimtex block diagrams. So as mentioned before, pneumatic plug doors are a very popular application. They've been the most popular type of door in the public transit industry. However, they are slowly being replaced with electrical drive plug doors. These doors feature accurate obstacle detection, easy installation, and require less maintenance, as checking for leaks in the pipes is not required. The below example shows a simplified block diagram of an electrical drive plug door system, where the voltage is 110 VDC. The power goes through an EMC filter first to filter out unwanted noise. 2 AM10 EWs convert the 110 VDC to 5 volts to power the controller and the motor. Having 2 separate converters for the controller and the motor helps isolate the interference coming from the motor. Next, we're going to be moving on to screen doors. Screen doors have been widely installed in major stations around the world. It prevents the passengers from falling off the platform and helps HVAC systems run more efficiently. The below system uses a pneumatic solution to control the door opening and closing. The system voltage is again 110 volts and features an UPS power supply in case of emergency. The input power goes through the first filter, which feeds directly into the motor. The second filter filters out the noise coming from the motor and sends 110 volts to the motor driver. The AM20EW converts the 110 to 15 volts and serves as the main power supply of the control circuit. The AMSRI a high-efficiency switching regulator steps down the 15 volts to 5 and powers the MCU. The isolated CAN transceivers are powered by the AM10CW to ensure the signal quality. Finally, an AM1LS converter serves as additional protection and powers the Hall circuit, which can be used to detect obstacles at the gate. Now moving on to train information displays. The information displays tell the passenger their current location and the upcoming station. The display receives the data from the train information system and displays it accordingly. As the signal line has to go through several cabins, it tends to pick up a lot of noise. The display unit must be designed so that it is immune to the noise and interference generated in all the railway environment. To ensure the information is displayed correctly, the below example uses an AMFW110 EMC filter to filter out the noise picked up by the power line. The AM75QB serves as the main power supply for the entire display unit. It converts the 110 volts to 24 and powers the LED matrix directly. An AMSRI switching regulator converts the 24 to 5 volts and powers the MCU, display driver, and 485 communication module. Finally, an AM1DR isolated converter is used to provide the power to the 485 signal line. The isolated communication module helps further reduce the chances of the display unit being interfered with. Now we're going to be talking about the Bogey monitoring system. The Bogey monitoring system monitors the bogey's status, including the steering angle, vibration, and temperature. The system can identify if there are any abnormal or possible failures on the bogey based on the data pattern that is sent out. As the traction motor is located within the bogey, the sensors are subject to extreme electromagnetic interference. Similar to the display unit, the monitoring system also uses an AMFW110 to ensure its electromagnetic immunity. An AM50QB, following the EMC filter, converts the 110 volt system voltage down to 15 volts and powers the bogey sensors. To add an extra layer of reliability, a second isolated converter, the AM15C, is used to power the MCU, HMI, and communication module. Now we're going to be looking at train VIP seats. These VIP seats are seats found in high-end cabins. Each seat requires an independent control system to control its position. The below seat control diagram uses a similar power solution as the bogey monitoring system. An AMFW110 is placed at the input of the system to provide the necessary EMC protection. An AM100QB is used as the main converter to convert the 110 volts down to 24 and powers the seat motors directly. Unlike the bogey monitoring system, the seat motor control wires do not span long distances and are not exposed to the same electromagnetic interference. Hence, the power of the control circuit is provided by the AMSRI switching regulator, which converts the 24 to 5 volts. This AMSRI is a non-isolated DC-DC converter. And finally, we're going to be looking at an operation monitoring system. The train operating system is the heart of the train. The below example shows a simplified block diagram of this system. The system implements an EMC protection device with an input overvoltage protection feature at the input. As the monitoring system needs to communicate with multiple devices on the train or the trackside, multiple isolated converters are used to avoid cross-interference between each input-output module. Thanks for tuning in, guys. Hope you learned something today. Again, Aimtec has a very large product offering of railway power converters that go anywhere from low power all the way up to 250 watts. If you have any customers that require power conversion for railway, be sure to check out Aimtec. Have a great day, and we'll see you in the next one.